So an impact test records the amount of energy that is absorbed by a specimen before fracture, which corresponds with its impact strength. For this experiment, we used a Tinius-Olson high-energy impact testing machine and filmed it with a GoPro Hero2 camera that records in 120 frames per second. We used the videos to measure how far the specimens traveled after impact, as well as the time in which they were traveling, so that we could determine their final velocity after impact.
Here is a simple diagram of how a Tinius-Olson impact tester works. And then given in the bottom right hand corner is an example of what a broken specimen looks like.
This would be a ductile specimen, as you can tell by the uneven fracture.
After testing, it was determined by the machine that the aluminum specimen absorbed 26 joules during the impact, and the low-carbon steel specimen absorbed 6 joules during the impact. Then, using that data and high-tech video analysis software, we were able to determine that the velocity of the aluminum specimen after impact was 1.614 feet a second, and the velocity of the carbon steel specimen after impact was 1.302 feet per second.
So as you can see, these are the specimens, the low carbon steel on the left and the aluminum on the right. They are, this is before impact. They are notched to create a stress concentration so that at impact they will fracture at that point. This is the after shot of the low carbon steel. As you can see, it fractured on a smooth plane. This indicates that the material is brittle. This is an after shot of the aluminum specimen. As you can see, it did not break on a smooth plane, but rather somewhat stretched or deformed, as you would see silly putty do if you tried to tear it. This indicates that this metal was more ductile.